I'm Patricio Winslow. I work at a startup called Lee Aerospace here in Buenos Aires. And this talk is going to be about using Go for real time safety critical applications. Um, there we go. So a bit of background about myself. I'm soon to be a mechanical engineer. So take all my words with a grain of salt. Not an engineer yet. Uh, I work at Lee Aerospace as a software engineer. And well, what Leah does is manufacture small satellite suborbital launchers. Our first launch was uh, small satellite orbital launchers. That's the goal. And well, our first suborbital launch was in January. This is a picture of uh, the team. We're those six in the middle. And my job mostly comprises rocket engine testing software and some flight software. So without further ado, let's talk about what the title parts mean. So the title of the talk is Go in Real-Time Safety Critical Applications. What is a real-time system? Well, Wikipedia sort of defines a real-time system as a system that has deadlines that have to be met or else. An example of a real-time system could be an aircraft. If the aircraft is landing on a runway and its attitude is askew, it can cause a problem or even an accident. This would be an example of a hard real-time system where the system response of the aircraft must correct those uh, misalignments to be able to land successfully. And missing a deadline to correct could mean a total system failure. So put simply, this means if a software executes a task too late, there's damage done for which there is no undo button. So we also have this term safety critical in the title. What do I mean by this? Well, again, Wikipedia, safety critical systems are characterized by the impact of failures, which tend to increase safety risk to people, environment, or machines. A failure can come in many flavors. It can be a mechanical malfunction, electrical failure, or software bug. I'll be talking mostly about software bugs since this language is centered around a programming language. So, a bit of context about where this software is going to be running, what its purpose is, because yeah, we're talking about using Go for real-time safety critical applications. And well, here we have sort of the case which we are trying to solve. Uh, in the diagram, you see what would be a schematic of a rocket-propelled vehicle. Um, so, and well, would you believe me if I said this was? Well, first of all, I'll ask you. What kind of system would you categorize this as? Keep in mind, using the terms we've just seen. Keep in mind we have two propellants, one next to the other. Uh, if these two mix, uh, yeah, catastrophes happen. They have a lot of chemical energy stored very near to each other. We have a rocket nozzle, which provides thrust, which we are trying to measure in our, in, or we are trying to use to propel our vehicle. And and between these propellants and the nozzle, we have injection valves, and these are what we control with our software. And these injection valves, if one of them opens too late during engine firing, it can cause detonation in the engine, causing the destruction of the nozzle and even the destruction of the whole system. So, given these facts, would you believe me if I said this was real time and safety critical, even a hard real time system? Uh, well, you better believe it. So, we are going to be controlling the system with an SBC that's running Linux, and this is going to be allow us to be able to run Go on it if we were to want to run Go. So, what does Go look like? After all this talk is about using Go. Um, so, for anyone who hasn't never come into contact with Go, I could describe it to y'all as a similar kind of C, similar to C. I understand most of you are experienced embedded developers, or maybe dabbled in a bit of C. So, uh, but and well, Go does have higher level constructs, but it does not have classes or inheritance. Due to this, it's often said that Go is not object oriented. Um, and so, looking at the first code bit in white, uh, here in Go we define a new sensor type, which is a struct, and it has a couple fields there to let us presumably interact with an I2C bus, write to a buffer, and then, well, making use of Go's higher level constructs, we can define a method on this type called getData, and which does so it grabs the bus of the sensor, performs a read on it, and presumably reads into the buffer. And then at the end of the function, we return the first item read in the buffer. So pretty simple, straightforward stuff, hopefully. This is going to be all of the code we see during this presentation. So on to why Go. So why would we choose Go for controlling a rocket-propelled system? To be clear, I'm not advocating for rocket software to be written in Go. This is simply a case study. Yeah, so Go for embedded systems. It's like speakers are getting bolder. Maybe next year I'll tell you all to use Windows, right? As far as I know, there is no safety critical software written in Go. If someone knows of any, I'd gladly welcome details on it. And yeah, about that, there are other tried and tested industry standard languages like Ada and C for these sort of safety critical applications. And Go is not even real time at its lowest level. It has a runtime and a pretty large one at that. And given these points, other languages seem like better fits, like Rust and C++, maybe. I did mention real time as a requirement, but with respect to other languages, we are really not sacrificing too much. Let me explain. Go is simple, and that's one point, and it's a big one. I work in a startup where time and manpower are a huge factor. The simpler it is to learn a language at a glance and understand at a code snippet at a glance, the better. At a startup, we're merely 5 people, and we're bound to have more engineers coming in. So, being able to teach and let other people grasp the language quickly is an important factor in deciding the technology to use. So that is one big reason. Now we'll talk about other important reasons why Go. So at the end of the day, we are controlling a mechanical system. Mechanical systems evolve 3 to 6 orders of magnitude slower than electronic ones. This means that Go approximates a real-time system as good as a C program would. In fact, there is no quantifiable difference if you were to program a rocket in C versus in Go, and no quantifiable difference in the rocket performance. So, for all intents and purposes, our Go is real time in our use case. Go also has excellent concurrent support. This is a huge deal in mechanical systems. We want to be able to spin up these virtual processes. We'll talk about called Go routines, um, fast, and not have to wait for these mechanical tasks to complete, which may take uh, hundreds of milliseconds. Um, yeah, so, and then we have also the garbage collected aspect. Now, garbage collection really sounds like something you wouldn't want in a flight computer, and you'd definitely be right in most cases. It is a liability. However, garbage collection also prevents a whole subset of insidious bugs from happening, and it lets us spend more time working, solving the problem at hand. And that is something valuable to have in a startup, as I mentioned. Time is uh, very important in a startup. And well, I've mentioned it, and I'll mention it again. It's a dead simple language. Um, so the compiler is dead simple as well. Like you, there's no compiler flags you have to fiddle with to get the program working. And yeah, and it also gives you also the simplicity combined with the strong typing of Go really provides you with confidence upon uh, making sweeping changes to your code base. This is something that is a property of many modern languages. I'm not sure how to describe it. Uh, Many of you maybe heard similar things from Rust engineers, Haskell, Elm, which who have this newfound confidence coming from these other weakly typed languages to perform huge changes and be sure that what they're doing is correct on the first regexp, as one would say. A huge other point I'd like to mention is the huge community. So time is money. We don't want to uh, spend time writing software we could defer to someone else, other uh, repositories on the internet written by uh, other people. So that's time we don't have to spend writing code and maintaining it. So deferring the writing of Rocket software is a questionable task, uh, but I mean, if you look, if you take your time to look, investigate what the library does on the back end, you and find libraries which have lots of stars, are tried and tested, are being used by other companies. You can find really robust libraries, and so this is a something great about Go is that it's all packages are on GitHub, are ready to be imported. There's no central packaging system. And okay, so we've talked about why Go, and well, after evaluating Go and seeing, okay, it is the choice we want to make, we program the software in Go, and we evaluate its impact. And we did have a software developed by third party before I was hired, so I'll be making comparisons to this software. And so the impact of Go. An unexpected benefit of Go was the noticeable lower power consumption. We went from 60% CPU usage on 4 cores to just 5% on 1 core. And I understand this is not an isolated incident, as I researched after. Uh, there's this link I'll leave down there. If you Google Mercado Libre grows with Go, that's a tongue twister. You'll see that Mercado Libre was able to reduce the amount of servers they had running, I think, eightfold. So, yeah, interesting little side note. And this is also a huge deal for Rocket software, since we are we are constrained by the amount of energy we have at our disposal. We usually have a battery on board which we rely on for small satellite launchers. And we also improved our sampling rate on all sensors. So we went from 300 to 1,000 samples per channel via SPI. The code base was reduced, although this might not be something you usually see with Go programs. It was maybe the haste in which the previous software was written, which led us to reduce it by three. And we were able to conduct 50 tests, 10 of them being live fire tests. And we've never saw a software bug or software failure. We did find many hardware failures, though that is to be expected. Hardware is hard. So overall, um, great, great results. And here's a picture of the motor firing, obligatory picture. So we were happy. We had successfully brought Go to real-time safety critical applications. And well, here is where um, I'll sort of leave aside the technical aspect of this talk and start talking more about a tool I found interesting, uh, exciting even, while after I finished developing the software. Uh, so after we finished the software and it was working, we looked around our test bench. You see, when you test the software, you also we have these small subsystems which run on microcontrollers, and these were programmed in C and C++. And it just got me thinking if you go for them. Uh, it just so happens you can. There is a Go compiler for microcontrollers. It's called TinyGo, and it's a project created by Eike van Latem. And we're talking about a whole new compiler, not extension. Uh, it's it's written from the ground up. And why is this? Why create a whole new compiler? It seems like so much work. Well, Go binaries, like native Go binaries, are humongous. A hello world binary surpasses a megabyte in size. Yeah, that might be pretty funny to some of you. But yeah, this is because in every Go binary, uh, the whole runtime is included, and that's a hefty runtime we're talking about. I mean, it provides you with a lot of services to your program, and well, TinyGo tries to remedy this by compiling Go source code using a reduced runtime. TinyGo's Hello World is only 10 kilobytes in size, which is 1% of the original. Only 10 kilobytes. Still, I mean, lets you program microcontrollers. So, I won't be going into much details about how it works, just to give you a little overview. Um, so, the first stage of the pipeline is very similar to the Go compiler, just tokenizing, parsing, and uh, conversion to SSA, which is a simplified version of your program. And then that SSA is fed into GoLVM, which converts it to the LLVM intermediate representation, which can then be optimized. And there's an interpreter in there, so to evaluate all the expressions which do not require inputs at before it is compiled to reduce the binary size. And so once its LLVM is done and compiled to machine code, we can flash to our port and to our microcontroller. And um, to develop with TinyGo, all you really need is TinyGo, Go, and Git. If you're using third-party libraries, and yeah, that's for most targets. Some targets require some third-party libraries. So why should I care about TinyGo? What is so cool about it? Well, it's starting to be I find it to be a very promising. It's being used by big companies like Fastly, though for web applications. One uh, huge plus point is that it brings with it the Go ecosystem, and that includes all the Go tooling, um, the libraries. So TinyGo is successfully compiling most Go libraries out there with no modification, and I just find that to be mind-boggling. I mean, it's compiling most of the packages under GoNum, which is like SciPy, NumPy um, for Go. And another huge plus point is its concurrency model. So these I talked I talked about a little bit about how great concurrency is with Go. So Go just you don't have to worry about threads. Basically, you can kick up these virtual processes called Go routines, and they pretty much I mean, the Go runtime and scheduler manages their lifetime, and you can worry about, I mean, solving the problem without diving too much into threads. And from the people I've heard who come from programming with threads in other languages, uh, they've been, uh, I mean, saved the head. They feel like it's a burden that's been lifted off of their shoulders. And with all these three little points I made, I believe it lowers the entry bar into embedded systems. And I'm going to make a bold statement here. C, C++, and Arduino, including libraries, are cumbersome to use. Uh, Downloading them, making sure the if defines the macros are set to your architecture and whatnot. CMake, yeah, this is all of this is out the window once you if you switch to TinyGo. Um, it's just so much easier to just get a program up and running. Though this is all the good stuff. I haven't talked about all the bad stuff yet. And well, yeah. So in spite of the benefits of Go, there is a caveat, as mentioned by one of the co-creators of Go. Go was not designed for embedded systems, so it's got some problems. And the most poignant of these is the required runtime, which performs task scheduling, garbage collection, and among other tasks, keeping track of types for runtime inspection. So this runtime talks with the operating system for the better part of these. What happens when you don't have an operating system? Well, that's where TinyGo takes matters into its own hands. So, by monumental effort, Eike van Latem, the creator of TinyGo, has implemented a limited runtime for TinyGo programs. For those not familiar with how a garbage collector works, it's or how to program a garbage collector, it is hard, and I mean hard. If you don't believe me, just ask Google. They have dozens of engineers working on the Go garbage collector, and every year they keep on making improvements and fixing bugs on certain architectures. And it's often been said that there is no one way to program a garbage collector. Each language has its unique implementation. In TinyGo's case, it was inspired by MicroPython's mark and sweep algorithm, uh, which is relatively simple algorithm, simple in quotation marks. The Go routines are another aspect of the runtime, which you can't have in these small embedded places. These we defer to LLVM. So what I mean is, um, Go routines are managed by the LLVM coroutine model. And lastly, we have other uh, runtimey libraries available in Go, such as mutexes, reflect, and the time package. All of these have to be implemented specifically for embedded systems. And there's also channels and other and the defer, recover, panic, uh, control flow scheme in Go, which is similar to exceptions. that also has a very particular implementation in TinyGo, always respecting the Go spec if possible. So now the question remains: can TinyGo be used in real-time safety critical applications? After all, that's the name of my talk, and I'll answer it with no. So the short answer to whether TinyGo can be used in real-time safety critical environments is no. The project is still in its infancy. LVM is also ironing out some bugs on certain architectures, and the garbage collector is still very rough. No, very is very strong. It's still rough around the edges. That said, it works incredibly well, and it's come a long way from the start of the year. Um, I remember I couldn't even get some programs running on AVR. That's all changed with LVM 11. Yeah, 11 I think. And if you're willing to push the envelope, there are some ways to strip the program of these liabilities with compiler flags. Uh, TinyGo offers the garbage collector, but you can choose not to disable it, and this will cause uh, you know it will error out your compilation if you try to make a heap allocation, and this way you can avoid these heap allocations and stay purely on the stack. But that's getting into the weeds. So conclusions: C and Ada have been used for decades, and for these safety critical systems, and they are still useful today. However, I see no reason why Go should not be used for mechanical real-time safety critical systems. As we have seen, it performs as well as its industry standard counterparts, and even delivers some high-level programming facilities not found in these other languages. What's more, I'd encourage engineers to keep Go on their radar, as it seems to be as it become seems to be becoming more popular by the day. Oof. And lastly, although TinyGo is not ready to control a rocket motor, it's still a great tool for non-safety critical systems. All right, thank you.